Well, welcome back. Today we're going to introduce the basics of fracture mechanics and the ways that we may use, techniques we may use to try to predict failure in materials due to crack growth. So we're going to look at a couple of things, and so you have these objectives. In class we're going to spend quite a bit of time looking at critical stress intensity factors, or K1C, approaches to predicting failure. We're also going to talk some more about the Sharpie transition temperature approach that you've been using in class, and we'll also do some plastic zone discussion, because it gives us some insight into what makes materials resistant to crack growth. So, why fracture mechanics? Well, fracture mechanics is a relatively young field. The first papers in fracture mechanics are actually written in the 1920s. I think 29 was Orawan's groundbreaking paper looking at cracks growing in glass. Now, that's not a particularly interesting problem because glass is not a structural material really, but it's a simple material, so that's where the work began. The real driver for what we know as modern fracture mechanics, that was World War II. And in particular, the failure of some of the Liberty ships. And the Liberty ships were a mass-produced freighter design, a bulk freight design that were prefabricated in large sections, brought to the shipyard and assembled very, very, very rapidly. For propaganda purposes, a Liberty ship hull was laid down and launched within 48 hours. Average construction time was like 5 days or so. But they could be built very quickly, and that was necessary because as at the opening of the war, the German U-boats were sinking tremendous numbers of Allied ships in the Atlantic. And of course, the United States did not fight in North America. Everything that we did happened at the other side of a large ocean, either the Atlantic or the Pacific. And so every soldier, every bullet, every can of beans had to be hauled over those oceans, and particularly in the Atlantic, those oceans were infested with enemy submarines and aircraft that sank a large number of the ships. So we needed to build tremendous numbers of ships very quickly, and the Liberty ships were actually designed, and their price, their cost to the government was such that they were estimated to have paid for themselves if they'd made a single crossing of the Atlantic and then had been sunk. So rapid production, and they used welded construction. Now, all the experienced shipyard workers were gone. They'd been taken off by the Navy to work on ships, or those that were young enough anyway, for service. And so you had a shortage of workers, and then suddenly you went from just a few shipyards in the entire United States. The shipbuilding industry had been allowed to almost disappear in the 1930s. And so there were only a couple of yards working, so they built something like a dozen shipyards literally in a few months. And so you had a tremendous number of new yards, new ways, and you needed new workers. So these workers came from the fields of the South and even of South Texas, and from rural areas where they'd been working in agriculture and primarily, and then women who left home and other office jobs and went to work in the yards. And so you had unskilled workers that had been newly trained. Steel production was running, steel mills were running flat out because you had to make ships and tanks and shells and all of the implements of war. And so quality of steel was declining, and these ships were not expected to last. Maybe if they lasted the war, that would be great, but then they were probably expected to be scrapped. And so they didn't worry too much about the quality of the steel. And when you combine all that with the cyclic loading of waves, as the ships would be pounding through particularly the North Atlantic, and the big square hatch openings, which created tremendous stresses at the hatch corners, combined with welds and defective welds from the new workers. So you had low quality steel, defective welds, design not optimized for long life with square corners and high stresses. All of that led to conditions where cracks would develop, and once they got to a critical size, they would literally race from one corner of a hatch all the way around the ship hull, back up the other side, and back to another corner, and they just would break in two. And there were about a dozen or so ships lost, and a large number that had to have major repairs to prevent catastrophic loss. So at some point, they were losing more ships or had more ships in danger from this than they did from the U-boats. By the time the war in the Atlantic had been won, this was a bigger hazard. Now, we didn't have any tools for really understanding why this was happening, and so in the 1940s and 50s, we began to see significant efforts in understanding how cracks grow in materials. The linear elastic fracture mechanics, the tests for that were first standardized in the 1970s. Nonlinear fracture mechanics, which really is key to very tough materials and understanding very tough materials, those first standards were not approved until the 1980s. 1981 was the first ASTM standard for nonlinear methods. And so these are relatively new. It's a totally new field, relatively new, and the really complicated problems in fracture, as you have in viscoelastic materials, or you have creep combined with fracture, those problems have not even been really mastered, and they're still subjects of tremendous amounts of research. So, new field, but we want to understand, why do cracks grow in materials? What's the driving force, and what can we do to stop them, and can we predict their growth? Maybe that's even more important. So fracture mechanics begins with a fundamental reality that we have a defect, generally a long, thin defect in a material. But across that defect, we have no load transfer. And what that does is it produces a stress state near the ends of the defect, that is, where the stress is much higher than in the far field. If you think about water flowing through a pipe, if you stick a plate in that flow, you're going to get tremendous acceleration of the flow around that plate. If you put a circular object or spherical object in the flow, you'd have much less acceleration because of the gentle nature here. The greater the acceleration of flow, by analogy, the greater the stress that you would see in a mechanical part under stress. You may think of stress as like a fluid that's flowing from bond to bond through the material. So we're going to have much higher stresses here than we would here. Even if these were the same width exactly, we'd still have that kind of breakdown. So you think about stress like water flowing through the solid. Now, so there's a couple of characteristics. In general, we're going to assume cracks are sharp. The tip here is a very small radius. And the key here is that a far field stress, a stress applied to the body out here, is going to cause this crack to grow. And even though we're going to call some of our methods critical stress intensity factor methods, what I want you to understand is that the controlling factor isn't that we've exceeded some critical stress. In all practical fracture mechanics, the real key is that the available energy, and it's the energy stored out here in the stressed material. You may think of the resilience of the material. When you've loaded it up, you've stored a lot of energy elastically. What's this energy that is stored in the material that is going to do the work of causing the crack to grow? And that work has two components. When you make a surface, you're going to increase the energy of all the atoms of that surface, and so you have to do work to make a surface. Also, you may have plastic deformation occurring, or viscoplastic deformation, and those processes consume energy, and so that work also has to be done. So there's a fundamental work that's required for fracture, and if there's enough energy in the structure to do that work, then the crack can grow, and if there's not enough energy, then the crack doesn't go anywhere. So we begin with the concept that flaws are stress concentrations, and in a general sense, this is the Griffiths equation. We have a Griffiths flaw that has a specified radius of the tip, and so you fit a circle to the tip of that flaw, and you ask what's the radius of that circle. That will be rho in the formula. Sigma 0 is the stress applied at a distance from the flaw, so we don't correct for the missing material at the flaw. We look at the far field stress. And then A is the characteristic length. And we see here a feature of fracture mechanics that's going to be continued in other equations. And that is an embedded flaw actually has two tips. And so the length that's applied to each tip is only half of the crack length. So this length is 2A. Whereas a surface flaw, all of this length is driving that one tip. So the length is A. So you have to be aware whether it's an embedded flaw or a surface flaw and use the proper value for your crack length. And so this is the Griffith solution. You see a relationship with the crack tip radius that's inverse. and a proportionality to the square root of the crack length. So the idea here is that the stress on the part, or in the material, as we approach the crack tip, the peak value anyway, is a function of crack tip radius and crack length. And so we plot that stress value as we get far enough away from the crack, way out here, we're at the far field stress. And then that stress rises, this 1 over the square root, you'll see in a little bit, 1 over the square root of r, to some peak value, sigma m. Now this is for a finite radius, generally a fairly blunt radius. Okay, and we have that at both tips. Now, that is called the Griffiths equation, and a Griffiths flaw has that clear radius. And you have general solutions for preventing fracture or failure by stress concentrations, and things that you will apply in mechanics of solids and in machine design and in structural analysis, where you have tables that allow you to calculate a stress concentration factor, KT, for a given geometry. And so if you go back to the Griffiths flaw, A over rho, the square root of all of that, times 2 is a stress concentration factor. That is, it's a single number, you can calculate a single number, that you multiply by the far field stress to get the local peak. And so this principle of the stress concentration factor you're going to encounter in numerous later classes. Now, we want to go beyond that idea. We want to focus on what's happening in a crack, not just a generalized fillet. And so we have to be aware that there is a crack tip blunting in real materials. In a perfectly elastic material that's perfectly brittle, a sharp crack will remain sharp. But in most materials, we're going to get some amount of plasticity. And what's going to happen is when we get a little bit of yielding at the tip, we're going to develop a radius. And in class, we'll look at silly putty and you can watch this process develop. But that is going to induce then formation of a radius that is not really, really small. Here the radius is approaching 0. Here we actually have a finite radius. And that's going to have the effect of reducing the stress intensity at the tip. It's going to give us a lower peak stress at the tip. So in general, materials that form plastic zones that permit some yielding of the material are going to create a much more favorable stress state because of this reduction in stress intensity. Now, again, to go back, understand that in fracture, the work of fracture is done by some external force acting on the structure or your specimen or whatever. And we can measure the amount of work done by measuring the force and measuring the displacement, and the product of those, or the integral of those, if they're not, one of them is not constant, is the work of that external force. So we find the area under the load displacement curve, and we have that work that's input. Now that work is input as elastic energy. However, that elastic energy may be spent in doing plastic work of fracture, or it may be spent using or creating the surface energy that's needed for a crack to form. So the key here is the external work has to be great enough to put enough elastic energy into the part to do the work of fracture in the plastic deformation regime and to create the surface area that's needed. And if we don't do enough external work, then we don't get this work done and a crack does not grow. So when does a crack propagate? The simplest approach is to say, well, it propagates when the applied stress is greater than some critical value. And for a purely elastic material, that value is going to be a function of the modulus of the material, because we're talking about how much energy is stored, divided by pi times the crack length, okay? And then gamma S is the surface energy, the energy per square inch or per square meter necessary to make crack surface. And so we can calculate from this what the critical stress is, that if we exceed that, if the near field stress exceeds that, we'll get failure. Now, this is a simplistic approach because we rarely have purely surface area energy or surface energy required, and so you might replace the surface energy with surface energy plus plastic energy, and you throw that in here for the gamma S, and you get something that makes a little more sense. So this is the Irwin approach to fracture prediction, but it is difficult to really generalize, and I think it's dangerous. Your book teaches it to you or shows it to you, but I think it's dangerous because you're thinking in terms of a stress, a cohesive stress. And as we'll see, the stresses are not quite as safe to play with, as that suggests. So let's look at what the stress distribution really looks like at a crack tip. These are the Westergaard solutions, just a couple of them. For the stress field ahead of a crack with a specified radius rho, and so here's your radius term here, there's the rho, okay? And this is in polar coordinates, so our position at every point outside or around the crack tip is a function of distance from the tip, r, and the angle theta. And so we have a polar description of the stress at every point out here. Now, the distribution gets very interesting if we look at theta equals 0. So if we let the radius go to 0, let's make this crack really sharp, and if the radius goes to 0, this term, let's look at sigma y, this term disappears, right, because it's a 0, this all goes away. And if we let theta equal 0, then sine of 0 is 0, so I have 1 here, and then cosine of 0 is 1, so that's just 1. So we end up with sigma y is equal to k over the square root of 2 pi r. That is the stress distribution as we approach, as we get closer and closer, as r gets smaller and smaller, is going to be quadratic. Right? We're going to rise as 1 over the square root of 2 pi r as we approach the tip. Now, so let's focus in on that. We get this equation, k over the square root of 2 pi r, where k is defined as the stress intensity factor. And so the stress intensity factor is simply some geometric parameter y times the applied far field stress, this is not the stress counting the crack, this is the stress as if there was no crack present, times the square root of pi a, where again a is that magic crack length that we need to know. So this is the intensity of the field, and this is the shape of the field. So stress intensity factor gives me intensity of the field. I'm going to go back here to this plot. All elastic materials that have a crack in them that's under stress will have a stress distribution with this shape, 1 over the square root of 2 pi r at the head of the tip. Okay? You're always going to see this curve. What varies depending on crack length and the applied stress is how high this curve is shifted up. That is, the intensity of the field shifts up or down with crack length and applied stress, but the shape is always 1 over the square root of 2 pi r. So we get the intensity is the k, the shape is 1 over the square root of 2 pi r, and this is the energy available. Essentially, this is the energy available in the near field to do the work of fracture. The idea here is if your k field that is applied to the structure is greater than some critical value, then the crack grows. If the k field applied to your structure is less than that critical value, then nothing happens. The crack just sits there and the structure is fine. Now, we think about this mathematically, what happens as r goes to 0. Well, obviously 1 over the square root of r goes to 0, this blows up to infinity. You can't have infinite stress, so what actually happens is the stress rises 1 over the square root of 2 pi r, and then it's capped at the yield strength of the material. Okay? And so this is the real behavior, which means unless your material is unable to yield at all, you're never going to have a perfectly sharp crack. There's always going to be some plastic deformation here which permits a crack tip radius to develop in the material. Now, how big is this crack tip plastic zone? Well, we can take the Westergaard solutions. We can go back to this solution. Okay, we're going to use this one, and let's let theta, or let's let the crack tip radius go to 0 just to make this term go away. So we're going to take this part of it, and let's set the stress in the y direction equal to the yield strength. And then let's solve for r to figure out how far away we have to go before we finally drop below the yield strength. Or another way to put it is, at what radius is the applied vertical stress, sigma y, exactly equal to the yield strength? That is, what's the limit of the yielded zone? And so when we do that analysis and do the rearranging, we end up with this expression. And you see that as the stress intensity factor increases, the plastic zone size gets bigger. Well, that's not a surprise. More and more stress, larger, more material yields, bigger plastic zone. As the yield strength rises, though, the plastic zone goes down, the size goes down, and in fact it's a square. So if you double the yield strength, you're going to cut the plastic zone size by 1/4. And so right in front of the crack where theta is equal to 0, this term goes away, and we end up with this very simple expression. Okay. But what we're defining is a region of the material in which everything inside of this region is yielded. Outside of that region, we still have elastic behavior, and the K field, the 1 over the square root of 2 pi r field, still applies. In here, that field doesn't apply. The stress is all equal to the yield strength. Okay? Now, we've seen that as you increase the yield strength, you decrease the plastic zone size. And so if we think about a Griffiths flaw, that ought to hurt our toughness, and in fact, that's what we see. As your tensile strength goes up, your Sharpie V-notch energy, which is one of your measures of toughness, drops. Okay, and this is somewhat quadratic, looks like. Definitely nonlinear. And so this is why we don't use the strongest material possible. As you raise the strength of materials, you dramatically reduce their toughness, and toughness is your insurance against unexpected problems. So you design to the required strength, no more, and you keep it just where you have to be to keep as much toughness in the structure as you can. It protects you against things you didn't know might happen. So what are the kinds of K problems that you're going to run into? Well, there's 3 categories, and essentially you're going to be solving for one of 3 constants in the equation. So for example, you have a part that's in service at a stress of 50 megapascals. Somebody's inspecting the structure and they find a surface crack of 3 millimeters deep and 8 millimeters long. The question is that crack dangerous? Do I need to shut down the service? And so the key here is, can you calculate what is the applied K, and then can you compare that to the material property K1C or K critical? Another kind of application would be you're making parts, maybe you're making pressure vessels or you're welding I-beams, and they're going to be inspected for defects. Now, you know the service stress you're designing for, and you know the shape or the kinds of defects you commonly make in your process. So maybe in welding, you know you're going to have an embedded penny-shaped flaw due to incomplete penetration of the weld or what have you. So now you're going to know the basic geometry, you know the surface stress, you know the material because this is what you're manufacturing. And the question is, how big of a flaw would be dangerous if this is my service stress? And then that's the flaw that I have to be able to detect. That's how good my X-ray machine needs to be. That's how good the eyeballs of my inspectors need to be. Here an inspector found a flaw. We're going to be checking these things, and the technique we use is going to depend on how small a flaw we have to find. Finally, you might run into a situation where you find a crack in a structure, and you measure the crack, and you know the material properties. And so the question is, well, you know, how big of a truck can we allow on this bridge? And do we need to downrate the loading of the bridge so people don't load it to an unsafe level? And so now you're worried about what is the allowable stress. So if you go back to the equation, let's go back here. Okay, basically the problems work out to be K is equal to Y sigma square root of pi A. You either are going to calculate the applied K based on a crack length and an applied stress and compare that to the material property, or you're going to have a material property and a known crack and you're going to solve for allowable stress, or you're going to have a material property and an applied stress and solve for an allowable crack length. And so you're going to work with these equations, or this equation, very simple, over and over again, just solving for the thing you don't know. Y is a geometry factor, and those will be given. It depends on the shape of the crack and where the crack is located. And so that's something you're going to look up, or that's going to be given to you in quizzes and exams. All right, so there's the K, and we'll do a couple problems in class. Now, when we ask, well, what are the criterion to measure the worst case behavior of the material, there's a couple of things to be aware of. If we change the temperature of the test, the critical value of K changes. And for BCC and HCP materials, that critical value kind of goes to a step transition. You're measuring this sort of in your Sharpie experiments. We'll talk about that more in a little bit. For FCC materials, in general, K declines with temperature. And for really, really strong materials, they're not strong. They're not tough at any temperature, and they'll probably be down here. But they all decline with decreasing temperature. The problem here is this is difficult to predict. And so, in general, if you need fracture toughness numbers at anything other than room temperature, you have to test at that temperature, the data, unless somebody's already done the testing for you, but it has to be temperature specific. Another question is the question of crack tip radius. And if your tip radius changes, it turns out the critical value of K also changes. Fortunately for us, that even as we get to sharper and sharper tips, eventually we reach a point where the K value quits changing. When we get to a sharp enough notch, what happens is when you load the crack, the first thing that you get is some yielding. The crack blunts to a common radius, and then propagation occurs from that blunted crack. So that's pretty sweet. Nature didn't leave us with needing to make infinitely sharp cracks. We just have to make cracks sharp enough for our given material to get us onto this worst-case plateau. We also find that as specimens change thickness, we see a change in the apparent fracture toughness. And we call this the plane stress, thin specimen region, and a plane strain or thick specimen region. This is simplistic. If you take a fracture mechanics course, we'll talk about what's really going on here. But what you need to understand is that specimens have to be thick enough to give you worst-case behavior if you're going to be taking that data and going to a large structure that is also very thick and which will therefore have plane strain or constrained behavior. If your structure is very thin, then it may be acceptable to use thin specimens, but you must be sure that your structure is not giving you worst case behavior. And it turns out it's a little more complicated than just the thickness of the structure. The last thing is that we need to be aware that as we change the speed of testing, K1C drops. So DEDT is simply the velocity of the strain per minute. And what we find is that K1C, or the critical value of K, drops as we change the rate. Now, why is this? Well, the reason for this rate dependence is that as you increase the loading rate, your yield strength and ultimate tensile strength tend to go up. So this would be an extreme case. For a small strain rate, we get a tensile behavior like this. As you speed things up, things get same modulus, but higher yield strength and higher ultimate and lower strain to failure. For metals, this range is generally quite high. This might be a 1 inch a minute, quasi-static test in the lab, and this might be 60-mile-an-hour impact in an automobile. So we're usually talking fairly large changes in speed. Going from 1 inch a minute to 2 inches a minute is not going to produce a large change in tensile strength or yield strength. But what happens is as your yield strength goes up, your plastic zone size goes down. Okay, now why does the yield strength go up? Well, if you go to high rate, you're not allowing dislocations to form or to move past obstacles. You're not allowing time for those things. So you're going to force those dislocations in, and things are going to happen at much higher stresses. Anyway, the point here is as your ultimate strength rises, your toughness is going to drop in the material. So strain rate is important. So we're going to define the critical stress intensity factor as the value of K when a crack begins to grow for mode 1, so opening mode, cracks pull open. Plane strain, that means thick specimens, thick enough to give us worst case behavior, and a sharp crack, sharp enough to give us worst case behavior. So this is what's implied when you see a K1C value, plane strain, sharp crack. If you're going to change the speed, the temperature, or even the environment, you can put it in water, you're going to have some corrosive media, you have to go do testing under those conditions. The K1C values that are going to be cataloged for you in a book will usually be quasi-static, room temperature tests, so very slow speed and at 25 degrees Celsius or so. So what do fracture toughness values look like? Well, here's on an absolute scale right out of your text. Metals are here, ceramics are down here, polymers are down here, and then composites, and these are all ceramic composites actually, look pretty good actually, possibilities of pretty high toughness. This is log scale, right? So there's a lot of compression here, and so it's a little deceiving in that regard. But when you think of plastics, you think of plastics as quite tough. So why are they down here with ceramics, which are not very tough? Concrete, which is just awful in terms of toughness. The thing to remember is that plastics don't have very great strength. You learned the strength of polycarbonates under 10,000 psi. So you're not going to put plastics under high stresses. At the stresses we apply, because remember K is equal to Y sigma square root of pi A, Y times the stress. At the low stresses we apply, we get low K values. If we get low K values, then we don't need very high K1C values, and things look fine. So The problem, or the thing about polymers is they don't carry a lot of stress, but the stresses they carry very well because they have adequate K1C for that. The problem for ceramics is that they're pretty strong. So we tend to want to put a lot of stress on them. They don't have good toughness, and so we see failure. The beauty of metals is that they're pretty strong and they're very tough, and so we end up using them up at high stresses, and we expect a lot of toughness out of them. The promise of composites, and we'll talk about this when we get to composites, is that we can get strengths like metals, actually strengths like ceramics, which are even higher than metals, and we can get toughness like metals, potentially. And so this is why all the interest in composites for very high strength, high temperature applications. All right, so how do we approach fracture? Well, we're going to learn in class linear elastic fracture mechanics. We're not going to learn elastic plastic. It's an extension, a lot of the same conceptual framework, just different parameters, different ways of calculating what's going on. So since we're going to teach you basics of LEFM, you'll understand the general framework by which we attack elastic plastic fracture mechanics. The other approach is called the transition temperature approach, and this is quite old and actually developed before World War II. And so the approach you guys are learning in lab is to use Sharpie testing to identify the transition temperature. So you've done this experiment, you have a Sharpie specimen. The thing to know about the Sharpie specimen is the dimensions are specified and the radius of the notch is specified. It is the same for all materials. It's supported. You impact it on this side. I hope you impact on this side or you get really bad data. And that peels this open and cracks the specimen in two. And then you use actually a very old design. I think Ben Franklin proposed something like this, and it predates him. We start with the pendulum at a known height. When you release it, it swings down, converting potential energy, mgh, the mass of the pendulum, times g times the height. Converts that to kinetic energy, breaks the specimen absorbs a lot of that energy, and so on the upswing it doesn't swing as high. This is the final height, and so this is the energy that's left in the pendulum, mgh on this side. So the difference in height times mg gives us the energy of fracture for the specimen. So a very elegant little test, and it's been around for a very long time. And so what we're going to do is you're going to plot the impact energy versus temperature, which you're doing in lab. FCC metals, you're going to see a general slow decline. For BCC metals, you're going to get a step change, and you're also going to see this in a lot of polymers, and you'll tend to see this in HCP metals as well. And then high-strength materials, generally not very tough to begin with, and they don't show a step change, okay, because we've suppressed yield so strongly now. So we're going to define the transition temperature one of three ways: fracture appearance temperature, midpoint in the energy, and the lateral contraction midpoint. Now, midpoint in energy would simply be to say, all right, where are we halfway between these two plateaus? Here we are. Okay, that's the ductile to brittle transition temperature. So that's the simplest way. And you're going to see graphs like this. There's a bunch of different materials. You see here's aluminum. 4340 in this case has been strengthened. Yield strength is very high, 200 KSI, and so you're going to this high strength material is going to see a decline in temperature in yield strength with temperature. And so you see the range of behaviors here. Now, if we do the lateral expansion analysis, you're actually measuring, you're all doing this in lab, how much wider the specimen is. And the wider it is, the greater the ductility. And so you'll get a plot like this. And then usually there is a specified amount of lateral expansion that defines the ductile to brittle transition temperature. There's also the fracture appearance temperature, and here you're looking at a range from absolutely brittle behavior to mostly ductile, 90, in this case, I think it's about 90%, so they say 79 here. So there's a center square here that's not quite ductile fracture. It's still very clear here. I'm sure these are the temperatures. So this looks to me like it might be 100%, whatever. Anyway, so you're going to, you can measure the shear lips, or you can estimate the amount of area that is still brittle fracture, because it's still sparkly, and you're going to plot that. Now, based on the different methods, here would be, they've assigned an arbitrary energy, 20 joules. Here's the amount of lateral expansion, and here's the 50% fibrous or 50% ductile appearing. And as you see, they don't give exactly the same estimate for temperature, okay, for the ductile brittle transition temperature. So you have to agree on which method you're going to use if you're going to use one of these techniques. Now, we want to talk about the limitations of the Sharpie test, and here's a problem that we run into. We look at the impact strength, which is normalized kilojoules per square meter of cross section, for different notch tip radii. Okay, so here's the 0.25 millimeters tip radius, 1 millimeter, 2 millimeter, whatever, for a particular material. This is not for all materials. And the problem here is that you see, obviously, the impact strength that I see depends on the notch tip radius very clearly here, right? Now, for this material, the 0.25 gives me probably acceptable behavior. But as I change materials, these curves shift, and 0.25 may not give me worst case behavior. And so we have to be aware of the danger of the notch tip radius being unconservative. Okay? And we're going to talk about that in a second. Also notice that as we change specimen thickness, here we're looking at energy per 2.5 millimeters of thickness, so they've normalized. We find that the dBTT curves, or the energy curves, shift, and more importantly, the transition temperature depends on specimen thickness. As we get thicker and thicker, okay, we get a higher and higher transition temperature. That is, the material appears brittle at higher and higher temperatures. It's got to be warmer and warmer to remain ductile. So this is problematic also. Okay, so be aware that your specimens, now this is 15 millimeters, so that's still your Sharpie specimen. Not much larger than your Sharpie specimen dimensions. You're talking usually 10 millimeters for the Sharpies. But obviously still not out of the woods here in terms of thickness. So here's the transition temperature as a function of specimen thickness for 3 different steels, and you see the temperature, and we go up, here's minus 70, and it can drop to minus 100, kind of levels out. So do we have a leveling out, okay, as things get thick enough? The question is, for a given thickness, we're not necessarily at the same place on this curve. Okay. So what happens? Sharpie dBTT is a nice technique. It's simple, but it may be non-conservative. Why? Your specimens have a specified dimension. They're thin, and your structure may in fact not be thin. It may be thick. So the specimens don't have constraint, therefore they behave like they're really tough. The structure has constraint, and so it behaves like it's really brittle, and you're going to over-predict the performance. Same thing with the notch tip. The notch of the Sharpie might be sharp enough to be worst case, but in tougher materials it's usually not. And real cracks, unfortunately, in real structures are usually sharp. So you have to use the Sharpie technique with quite a bit of care, because the specimen is not necessarily representative of worst case behavior in the structure. That being said, there's a lot of value. You get data like this. What's the effect of sulfur on the ductile brittle transition temperature? We see a shift in the temperature. You also see the shift in the plateau as we go to cleaner and cleaner materials. It's much higher and higher toughness, okay, at both below the transition temperature and above. And so you might use dBTT design in this way. Once you've identified the ductile brittle transition temperature, you're going to modify your allowable stress. So let's say you're 40 degrees above the dBTT. You can use your allowable stress, whether that's a yield stress or an ultimate stress, whatever, you just use it. As you get closer to the dBTT, let's say 30 to 40 degrees above, you're only going to use 90% perhaps. 20 to 30, 75%, 10 to 20, a half, whatever. So you'll have a criteria that will not allow you to design within 10 degrees of the ductile brittle transition temperature. Now, if you go back and look at how some of these can shift that dBTT, you see if your specimen is, let's say, a 10 millimeter specimen, that dBTT would be at 60. A 15 millimeter specimen is going to be at about 18 degrees or 17 degrees higher, right, 70 something. And so you got a 17 degree shift from the true worst case behavior because you're at 10 millimeters and your material's not worst case until 15 or larger. So you could easily overwhelm this 10-degree margin and find yourself operating here when you probably shouldn't be working here at all, because you may be well into the brittle behavior. Anyway, so this is, again, this is not a code someplace. You're going to have a criteria based on your company's experience, but it's how you might use DBTT in design. So that's it for fracture mechanics. We'll be doing a lot of problems in class. Hopefully you will master these relatively simple techniques. Conceptually, this is a very rich topic. In terms of computations, it's actually quite simple. But it's a very powerful tool for understanding failure, preventing failure, predicting failure in the presence of flaws in your structure or your parts. Until next time, have a good day.